Today we're going to be cracking one of the most elegant and powerful codes in all of science, the periodic table. And, it all really starts with a very fundamental question. How do you find order in chaos? I mean, it's a question we face every single day, right? Whether you're just trying to sort your thoughts or tackle a mountain of laundry. Well, for centuries, scientists were facing this exact same problem, but on a cosmic scale, with the actual building blocks of the universe. Let's think of it like this. A messy closet, it's just pure chaos. You can't find anything, there's no system, it's a nightmare. But an organized closet? Oh yeah. Everything has its place, and finding what you need is, well, it's effortless. This simple idea, this move from chaos to order, is the key to understanding why the periodic table was such a revolution. So before the 1860s, the entire world of chemistry was basically that messy closet. Scientists knew about a whole bunch of elements, but there was just no system, no rhyme or reason to how they all related to one another. It was a total mess. And get this, they had 63 different elements to work with. I mean, imagine that. 63 different items, each with its own unique personality and properties. It was just this jumble of facts and figures waiting for someone, anyone, to come along and make sense of it all. And that someone was a brilliant Russian chemist named Dmitri Mendeleev. He was actually a professor writing a textbook, and he was getting so frustrated, he was determined to find a logical way to present these elements to his students, to finally clean up this cosmic closet. The key piece of information he decided to zero in on was something called atomic mass. At the time, this was really the best way they had to measure and compare the different elements. It's basically just how heavy an atom of each element is. His method was just so clever and simple. He created a card for each of the 63 known elements, kind of like a trading card, with its name, its atomic mass, and its properties. And then he played a sort of chemical solitaire, arranging and rearranging them over and over, just looking for some kind of hidden pattern. Until finally, he tried ordering them by increasing atomic mass. And then, wow, the breakthrough. A stunning pattern just appeared right before his eyes. As he laid out the cards, elements with similar behaviors, things like being soft metals or reacting violently with water, they started to naturally line up in the same vertical columns. He'd done it. He had found the hidden rhythm of the elements. But here is where Mendeleev's work goes from just being clever to being pure genius. Because his table wasn't just some neat list. It was a predictive tool. It was like a map to the future. See, he was so confident in his pattern that when an element didn't seem to fit, he didn't try to force it. Nope. Instead, he just left a blank space, insisting that an element had to exist to fill that spot, even though nobody had discovered it yet. I mean, can you imagine the reaction to that? You present your big discovery and it has holes in it? An incomplete chart might look like a failure, like a huge mistake. But for Mendeleev, he saw it as an opportunity. He saw it as a guide for future discoveries. And he didn't just leave a gap. Oh no, he made incredibly specific predictions. For one of those gaps, he basically said, okay, an element exists right here, its atomic mass is going to be around 68, and it's going to be a soft metal just like its neighbors in this column. So bold. And sure enough, just a few years later, the element's gallium was discovered. Its atomic mass, 69.7, and its properties, a soft metal. Mendeleev's prediction was just stunningly accurate. His table could literally predict the future of chemistry. Amazing. So, Mendeleev's incredible foundation led directly to the modern periodic table that we all use today. It's a version that's even more precise, and it's all thanks to one really important update. So what was the one key change? Well, while Mendeleev used atomic mass to organize everything, the modern table is organized by atomic number. It's a subtle difference, but it's absolutely fundamental. And what is the atomic number? It's simply the number of protons in an atom's core, its nucleus. And this number is like a unique fingerprint for each element. No two elements have the same one. This turned out to be the true, fundamental organizing principle of the cosmos. Okay, so this is where the table's real power gets revealed. It doesn't just list elements, it explains why they behave the way they do. So why do elements in the same column, or what we call a family, act like siblings? What's the secret? Well, the secret lies with something called valence electrons. Now, these are the electrons in the outermost shell of an atom. You can think of them as the social electrons. They're the ones on the outside, the ones that interact with other atoms. They drive pretty much all of chemistry. And here is the biggest rule of the game. Atoms want to be stable. And for most of them, stability means having a full outer shell of 8 valence electrons. This desire, this need to get to 8, is what makes some elements desperate to react, and others perfectly happy to just be left alone. So with that in mind, let's take a quick tour of the table and meet a few of its most important chemical families. It's kind of like touring a city and visiting the different neighborhoods. So broadly speaking, the whole table is split into 3 main classes. Over on the left, we have the metals. They're shiny, they conduct electricity, and they're malleable. On the far right, you've got the nonmetals. They're often dull, brittle, and poor conductors. And then, kind of wedged in between, are the metalloids, which have properties of both. All right, let's get specific. Meet group 1, the alkali metals. These guys have only 1 valence electron, and they are absolutely desperate to give it away to get to a stable state. This makes them wildly, extremely reactive. I mean, sodium, for example, will literally explode if you drop it in water. Now, way over on the other side of the table, we find their perfect partners. Group 17, the halogens. They have 7 valence electrons. They are just 1 electron away from that stable set of 8, so they are desperate to steal an electron from another atom, which makes them just as reactive as the alkali metals. And finally, we have the cool kids of the table. Group 18, the noble gases. With a full outer shell of 8 valence electrons, they've already got it made. They're perfectly stable. They don't need to gain any electrons. They don't need to lose any. They are just content, aloof, and almost completely unreactive. So, you see, the periodic table is so much more than just a chart on a classroom wall. It's a map of the known universe. It's a testament to our search for order and chaos. And it's a story that's still being written. With scientists creating new, super heavy elements in labs, it really makes you wonder, what chapter will be written next?